Welcome to this tutorial on confronting issues of scale in socio-environmental systems modeling. I'm Xiaoxuan Rose Wang, a senior research scientist in the Ecological Systems Laboratory, housed in the Department of Ecology and Conservation Biology at Texas A&M University. I also serve as co-editor-in-chief for the international journal Ecological Modeling, whose scope includes papers describe the development and use of models of socio-environmental systems. This tutorial builds upon concepts presented in the paper and associated succinct video titled Grand Challenges in Socio-Environmental Systems Modeling by Dr. Sandas L. Sawa and colleagues. I will also draw upon two papers that resulted from discussion during a recent succinct pursuit workshop, for which Dr. John Little of Virginia Tech University and I were principal investigators. In this tutorial, we will describe the types of scale issues that arise during the various phases of the socio-environmental modeling process and suggest how to deal with them. If you are new to the modeling of socio-environmental systems, I strongly encourage you to watch the 3-part tutorial called Building the Basics for Socio-Environmental Systems Modeling. Each part is fairly short. The use of socio-environmental systems modeling as part of integrated environmental assessment has become increasingly common in recent years. Most often, several models from different scientific disciplines are integrated with the aim of providing a single, holistic model that can be used to help inform the decision-making process of resource managers or policymakers. As you might guess, the integration of models representing different kinds of systems developed by scientists with different disciplinary backgrounds is not a trivial task. One challenge that almost always arises is related to integrating or connecting the scales at which components and processes in the various models are represented. For example, some biophysical processes might occur slowly and affect large areas. Some might occur rapidly and affect small areas. A policy decision might have a global impact almost instantaneously. Imagine a model that needed to include climate change, local weather patterns, and agricultural policy decisions affecting crop production in the U.S. Great Plains. This dynamic process occurs on markedly different spatial and temporal scales. We will address issues related not only to mismatches in spatial and temporal scales, but also those related to mismatches in organizational scales. Organizational scales are no less intuitive than temporal or spatial scales, but are trickier to define precisely because we have no universal unit of measure with which to define them. For example, individuals can organize into groups, and groups can organize into large organization units. But we might define the groups formed by individuals as family groups, or social groups, or sport teams, and the organizational unit formed by groups as companies, or political parties, or countries, depending on the problem being modeled. The most fundamental scale issue in any systems model is to ensure that scale choices for model components are compatible with each other and are appropriate given the purpose of the model. A good example of the challenges comes from a USDA project modeling pest management of the invasive sugarcane aphid, which affects the grain sorghum. It illustrates how socio-environmental systems models typically include representations of different model components. The processes driving the dynamics of those components are often at different levels of abstraction, with different levels of detail and different scales. What would be the scale of an integrated model? The most fundamental scale issue in any systems model is to ensure that scale choices for model components are compatible with each other and are appropriate given the purpose of the model. Here, we see a multi-scale representation of a dynamic landscape. Suppose for a moment, we were interested in modeling management strategy for controlling the balance of woody vegetation or brush versus grass in a prairie community, rather than including leaf dynamics driven by photoperiod or landscape dynamics driven by climate change in our model. It likely would be more desirable to represent the ecologically driven changes in vegetation from prairie grass to woody brush in terms of monthly change in grams per square meter. We might summarize those changes at the community level in terms of annual changes in the relative amount of brush present, perhaps in terms of the percent of the area under the crown of brushy vegetation or brush canopy cover. That is, we will convert grams per square meter into percent canopy cover. This coarse scale representation likely would be more useful than finer scale representations, given the overall focus on modeling management strategies. Finally, we might prescribe rules by which different types of land managers will monitor and react to changes in brush canopy cover. Perhaps public land managers will monitor only once every 3 or 4 years, and if canopy cover exceeded a threshold level, they will use controlled burning to remove the brush the following year. Perhaps private ranchers will monitor every month, and if canopy cover exceeded their threshold level, they will reduce the brush by burning as soon as possible. That possibility might depend on burning regulations imposed by an organization in each county that monitors daily local weather report and imposes county burn bans, or by a state legislative organization that every 2 years reconsiders the legality of burning throughout the entire state. In social-environmental systems modeling, coupling processes operating on different scales involves both a computer programming aspect and a conceptual aspect. The programming aspect needs careful attention, but we have software available to help us accomplish this task. Regarding the conceptual aspect, we face the complexity paradox, or the trade-off between realism and uncertainty. If we choose a fine-scale representation, we increase realism. But with more parameters to estimate, we also increase uncertainty. If we choose a coarse-scale representation, we decrease uncertainty, but also decrease realism. Another conceptual consideration is to ensure the compatibility of fine-scaled and coarse-scaled representation. That is, the manner in which information is aggregated and disaggregated as it is passed from one scale to another must be conceptually sound given the purpose of the model. But who ensures the scale choices are compatible with each other and are appropriate given the purpose of the model? Well, the modelers, of course. But who are the modelers? The modelers are all of the people involved in the modeling process, which usually includes not only an interdisciplinary group of scientists, but also a multi-vocational group of stakeholders. Social-environmental systems modeling is a social-technical process. By that, we simply mean the process by which the modelers choose scales and decide how to implement their scale choices in the computer. Such choices are influenced by the expertise, experiences, biases, beliefs, and social values of each modeler, all of which also affect their perception of the purpose of the model, the information upon which to base model development, the policy question to address, and the scenarios to simulate. It is impossible to overemphasize the importance of this social-technical process. Scale issues arise throughout the modeling process. As we saw in the first tutorial of this series, we might think of model development as passing through the general phases. Essential to defining the problem and conceptualizing the system is the involvement of stakeholders in the process of bounding the system and identifying appropriate scales. I hasten to add that almost always we progress through these 4 phases in a 2-step forward, 1-step back fashion. As we reflect on where we are, we often decide to return to an earlier phase to reconsider our decision. In socio-environmental systems modeling, quite often the decisions we reconsider are issues of scale. In this tutorial, we identify the types of scale issues likely to arise in each modeling phase and suggest how we might deal with them. But, again, please keep the interconnectedness of these phases in mind, and hence the multi-phase nature of scale issues. We often become aware of a particular scale issue only after the modeling process has progressed beyond the point at which that scale decision was originally made. Most commonly, objectives are focused on trying to predict what might happen to systems in the future under some particular set of circumstances. While the general objectives as originally stated often seemed clear enough, initial discussion among modeling team members usually reveal obvious difference of opinion in terms of the scales at which different aspects of the system are perceived. For example, team members might all agree that system response to climate change is the issue, but disagree on climate scenario to explore and the system component upon which to focus attention. We mentioned earlier that the modeling team often includes not only scientists, but also stakeholders. Decisions regarding the diversity of stakeholders to include are influenced by the perceptions of the initial members of the modeling team, and by initial interest groups, such as those commissioning the work. Discussion and disagreement regarding the experiences, biases, beliefs, and social values that should be embodied in the group of stakeholder members of the modeling team are themselves issues of organizational scale in that they ultimately affect the scope of the project. Establishing boundaries for the system, and hence the model, consists of separating those components that we think should be included within the system from those that we think should be excluded. We do not want an unnecessarily complex model, but likewise, we do not want to exclude components that might be critical to the solution of our problem. Obviously, this is a highly subjective procedure and usually is a subject of much discussion. It is common to define and redefine system boundaries several times as we are developing our conceptual model. Having established initial boundaries for the system and identified those components we think should be represented explicitly in the conceptual model, our focus shifts to determine the most appropriate scale or scales at which to tackle the problem at hand. That is, we determine at what scales the model component and the processes can be most usefully conceptualized. The components and the processes included in the conceptual model are, of course, based on the perception and the priorities of the modelers. Thus, the scale issues encountered during conceptual model development often arise from the different scale lenses through which members of an interdisciplinary team view the model. Hence, the challenge is to establish a shared language among team members, which will allow reflection on how their different scale perceptions can be integrated into a coherent, multi-level conceptualization of a system of systems. The development of guidelines to aid in this type of reflection and integration is currently an active area of investigation by socio-environmental modelers. Scale issues arising during conceptual model development also are closely associated with differences in the scales at which the available data, information, and knowledge have been collected, and all are usually discussed. Common issues include assuring the compatibility of finer-scaled quantitative data and coarse-scaled qualitative information, as well as dealing with the lack of available data at the desired scale. Thus, scale decisions must be made within the context of the scales at which information can be collected. Transparency in the collection process is necessary to ensure that information collected at one scale can be interpreted appropriately across the range of relevant scales. Transparency within the context of data collection and usage also is a key factor in developing trust among stakeholders and model users. Here, it is important to note that different types of data are used in different ways during model development. Some data are used to drive the model in the sense that they create the external conditions within which the model processes occur. Climate data provide an example. Other data are analyzed to parameterize model processes. Data relating plant growth rate to environmental temperature provide an example. Yet other data, which have not been used in model development, are used to validate model output. Data on plant biomass at monthly intervals provide an example. Of course, data credibility is prerequisite for all of these uses. That is, we must have confidence in the reliability of the data at the scale of its use. Modelers from different disciplines may also utilize different scales for the same process, resulting in inconsistencies and thus errors, the source of which are difficult to identify. In this regard, non-quantitative sources of information gathered from literature and all through stakeholder engagement may become key assets that resolve such issues. The documentation developed in the scoping phase can be leveraged to ensure applicability and validity with regard to the model purpose. In cases where data describing a particular linkage in a socio-environmental systems model are not available, theoretical relationship, generally applicable empirical relationships, or model processes and outputs can be useful representations for the purpose of the socio-environmental systems model. During the phase of quantitative model formulation and evaluation, scale issues can occur in the steps of quantitative integration, model calibration, uncertainty analysis, and evaluation. During quantitative model formulation, scale issues often arise when the component models lack modularity and hence both syntactical and semantical consistency. This is a fancy way of saying that the component models lack clearly defined interfaces that facilitate the transfer of information from one model to another in a manner that does not misrepresent its meaning. The development of guidelines to aid in the modular design of models is another active area of investigation by socio-environmental modelers. Elaborating a bit more about syntactical and semantic consistency, the existence of a computerized coupling between two component models does not guarantee an appropriate maintenance of the conceptual content of the information. Imagine for a moment a mermaid, who is of course half human and half fish. Now, imagine a creature that also is half human and half fish, but with the head of a fish and the legs of human. Doctors Voynov and Sugar used this image and coined the term intergrunsters to emphasize the point that two models could be computationally coupled but be contextually inappropriate. Calibration is the process of adjusting parameter values or altering the functional forms of equations to achieve more reasonable, more useful model behavior. Of course, values of model parameters should not be adjusted outside of realistic ranges, which are not necessarily scale-dependent. In multi-scale socio-environmental systems models, technical scale choices during model calibration will affect not only the accuracy of the calibration of a compartment model, but also the level of error propagation throughout the integrated model. So whenever possible, the scale decisions in a component model should consider the effect on output uncertainty of the integrated model, at least qualitatively, and if possible, quantitatively. Socio-environmental system models often target large problem domains that need complex, multi-component models for their assessment and by their nature have a high degree of uncertainty. This uncertainty results not only from an increased number of parameters per se, but also from an increased number of interactions among component models, which likely are operating at different scales. Tracing the propagation of uncertainty within and among component models is a challenging endeavor, and uncertainty analysis is another active area of methodological development by socio-environmental modelers. Here, I use fire management as an example. When the model purely depends on grass brush competition, you can see the green line with some uncertainty range. However, after adding a human perspective into the model, you can see the red arrow has an added-on effect on the green line and potentially adds more uncertainty by shifting the green line toward the black line. Turning our attention to the application phase of socio-environmental systems modeling, a critical consideration is that component models may evolve independently. Development of each component model, by necessity, is led by disciplinary experts, and most likely these models will undergo separate, asynchronous development cycles. I want to mention two aspects of these separate development cycles that affect, first, appropriate implementation of the integrated model, and second, model persuasion and communication to stakeholders. Appropriate implementation of the integrated model may be hindered if component models evolve independently, because changes being made to one model may not be well matched with changes being made in another model. For example, consider an integrated model for control of vector-borne diseases composed of an ecological model and a management model. Further, suppose the ecological model assumes there is only one host for the disease vector, and the disease control model focused exclusively on controlling the vector on that host. If discovery of a second host prompts inclusion of this new host in the ecological model, continued elaboration in the disease control model of strategies focused exclusively on the initial host would preclude appropriate implementation of the integrated model. By model persuasion and communication to stakeholders, we mean facilitating future use of the model and ensuring that it is used appropriately, that is, as it was intended to be used. This depends, of course, on consensus among stakeholders and the modelers as to model purpose. We focus here on the scale of documentation and the process of evaluation required in socio-environmental systems modeling. When socio-environmental systems models are used by external stakeholders, some amount of technical support and adequate documentation and user-friendliness are likely expected. Without this, use of the model and thus its impact is likely to be minimal. Now that we have reviewed scale issues throughout the modeling process, I would like to provide some general suggestions for dealing with scale issues that arise during socio-environmental systems modeling. My colleagues and I have gleaned these suggestions from our own experiences and from the experiences that others have reported in the literature. Arguably, their applicability extends beyond issues of scale per se, but we think they are particularly relevant to scale issues encountered in socio-environmental systems modeling. They include 5 pieces of advice that are simple and commonsensical. Yet, it often is challenging for interdisciplinary groups of modelers to put them into practice. First, we suggest that as a team member, you foster constant collaborative learning and reflection. Discussions along the way of how the team model building process is going will help the team build trust and ensure integrative model formulation. A diversity of perspectives on the problem at hand is a strength of interdisciplinary, intersector groups, but also is a potential source of strife. Effective and reflective communication is a prerequisite for development of a cohesive model of a socio-environmental system. In our experience, the most efficient way to move an interdisciplinary conversation forward is to look backwards, in search of shared concepts. Once we have found common ground, we can move the conversation forward along diverse disciplinary paths under the guidance of our disciplinary experts, each of whom they can explain where they are leading us and why. Related to effective communication among modeling team members is effective documentation of the modeling decisions made during team discussions. Although a variety of documentation guidelines applicable to socio-environmental systems modeling, including description of spatial and temporal and less commonly organizational scales, most focus on detailing final scale choices. No mention is made of potential alternative scales and whether they were discarded as inappropriate or remain potentially viable alternatives. However, there has been increasing recognition of the importance of documenting the discussions at each important decision point during model development. When properly documented, the content of these discussions can provide both guidance and justification for the pathway of model development. In particular, detailed explanations supporting scale decisions can reveal the richness of thought embodied in these decisions, which otherwise likely will be forgotten. Thus, when asked by end users to explain how specific scale choices were made, modeling team members will be able to recapture the richness of their decision-making rationale. This ability to communicate scale decisions clearly increases model credibility and usefulness, and also facilitate reflection on scale decisions in response to questions about alternative scale choices. Debates related to scale decision in socio-environmental system modeling often are related to a mismatch in our perception of causality. Thus, explicit acknowledgement of the subjective nature of causality is a requisite for constructive discussion of scale issues. When we look at a particular relationship in our model, we likely will perceive it as an explanatory representation that embodies cause and effect, or as a phenomenological representation that is basically correlative. We are satisfied as long as our perception of the current representation matches our expectation of how the relationship should be represented. If the relationship falls within our area of expertise, we probably would argue that a scientifically credible representation must be explanatory. and to be explanatory, it must include a lot of details. If the relationship falls outside our area of expertise, we probably would perceive a much less detailed representation as sufficiently explanatory, or simply would not see the need for an explanatory representation. Obviously, different team members are likely to perceive the representation of any given process differently. We suggest that it would serve modeling teams well if their members explicitly acknowledge the subjective nature of their perception of causality at the very beginning of the modeling process. A discussion focused on the concept of a continuum of levels of subjectively perceived causality is time well spent. The initial response to such a discussion almost surely would be, "Everyone already knows that," which probably is true enough if viewed as an abstract concept. But based on our experience, we are quite sure that if early discussions among modeling team members were documented and re-examined, it would be obvious that the subjective nature of defining causality is seldom recognized in practice. As we progress through the phases of model development, we should reflect often on where we are and where we have been, and embrace the opportunity to reconsider the decisions we have made. Obviously, the effective documentation of modeling decisions, which we mentioned a moment ago, greatly facilitates this. In socio-environmental systems modeling, often the decisions most likely to benefit from frequent reconsideration are scale decisions. Our reflections might motivate new insight that emerge from the discovery of new information, or from discussions among modeling team members using an enriched, more fully developed, shared language. This new insight might suggest relative minor rescaling involving particular variables or functions, or major rescaling involving linkages among the social and environmental model component, or even modification of project objectives and the rescaling of system boundaries. By nature, our willingness to make changes tends to be inversely related to the size of the required one step back, and likely also is diminished by our uneasiness about publicly admitting we made a mistake. A cultural shift in thinking that embraces and rewards adaptive adjustment throughout the modeling process, which could be facilitated via documentation of the rationale for those adjustments, would be of great benefit in dealing with issues of scale. Embracing change in socio-environmental systems modeling entails the testing of model integration, especially the regular testing of linkages among physical, biological, and social model components. Such testing should include conceptual as well as technical aspects. The ability to write code that links model component in a computer is a necessary but insufficient prerequisite for appropriate model integration. Technical challenges to integration arise when component models have been developed using different spatial, temporal, and/or organizational scales. Often component models have been calibrated independently of one another, which, in addition to requiring the rescaling of information passed among models, may also require recalibration of the newly linked models. The new linkage also may give rise to rescaling issues within the newly linked models. Conceptual challenges to model integration are ever present, but are easily overlooked, and the conceptual aspect of scale issues can be tricky to identify precisely. In socio-environmental systems modeling, most frequent component models have been developed originally to address questions that differ from the questions being addressed by the integrated model. That is, component models were conceptualized, developed, and validated for use within different domains. Thus, Their reuse within the new domain of the integrated model requires revalidation, which includes evaluation of their conceptual validity or credibility within the new domain. Regular shared language discussion focus explicitly on scaling differences among physical, biological, and social model components, facilitate early identification and the resolution of both technical and conceptual mismatches, and is time well spent. And this brings us to the end. Thank you for joining, and thanks to the entire Socio-Environmental Modeling series team for the invitation to develop this tutorial. And a special thanks to SESync for their extensive script editing and the video graphic production. I would also like to acknowledge all the members of the SESync Pursuit Synthesis team and the colleagues from USDA AIS project, area-wide pest management of the invasive sugarcane aphid in gram sorghum, whose names are listed at the end of this video just after the resources for future study. In closing, I will just remind you that this tutorial is an outcome of the SESync Pursuit, titled Simultaneous Managing Scale and Uncertainty Using Innovative Software Design Concept in a Tiered System of Systems Modeling Framework.